Hello everyone, my name is Karin Wolff and my postdoctoral research looks at engineering problem solving across engineering sectors. Now, the key driver has been to identify what it is that we are doing or should be doing in higher education to deliver the problem solving engineering practitioners this country desperately needs. I'm going to briefly touch on the realities of this problem as well as the original PhD research tools, and then use this to zoom into some interesting data on how the manufacturing sector is responding to what some have called a crisis. Now, fact number one, I don't think this comes as a surprise to anyone, but we have 7.5 million unemployed people that would be counted as part of the South African labour force. Now, South Africa has had an unemployment rate in excess of 20% for the past 2 decades. Compared to our BRICS counterparts, this is seriously problematic. Fact number two, of the top occupations in demand, science and engineering professionals rank 3rd highest. And yet, we have 10,000 unemployed technicians at the last count. These were 2013 statistics. We have 65% of all eligible workplace learning students on diploma routes being unable to find workplace learning, and one of the key reasons is the lack of required technical skills. Now, this is not a unique South African problem. 34% of over 40,000 employers surveyed across 42 countries cited the lack of required technical skills as the key reason for being unable to appoint graduates. Even among the employed, 70% of executives in an international survey say technological skills are a major problem. Fact number three, we have very low numbers of tertiary educated adults in South Africa. So let us be in no doubt that we need the numbers in the TVET and higher education sectors, and that we need to address the lack of technical and technological skills desperately needed for the economy. So this is a comparative picture of our enrollments and graduates in engineering across institutional types. We're not producing enough, and what we're producing is not deemed good enough or equipped for 21st century engineering practice. So my key research was sparked by this issue of how do we better prepare graduates for 21st century engineering work? Now, because I wanted to speak back to the curriculum around the issue of the theory-practice divide, I went into industry and looked at what existing employed graduates, primarily technicians, actually do. I wanted to see how they work with the core theoretical knowledge of the curriculum in actual real-world practice. So the PhD study focused on mechatronics engineering. It represents a really good mix of the kinds of disciplines that form the basis of many science-based professions, but it is also entirely dependent on computer-based automation and control technologies, which have evolved exponentially over the past decades. Now, given this relationship between so-called stable sciences versus dynamic technologies, I believed we needed a better understanding of this synergy. So for the purpose of my original research, I generated problem-solving maps based on how technicians effectively solved technical problems, drawing on what kinds of knowledge. And I concentrated on eliciting or pulling out physics, mathematics, and logic. Now, the analytical tool I used comes from the sociology of education, specifically legitimation code theory. Now, this one is part of a dimension called specialization. What makes knowledge what it is? Now, this plane is called the epistemic plane, and quite simply, it enables us to look at knowledge practice itself, how we approach what. Now, the vertical axis, the so-called ontic relations, refers to the boundedness of a phenomenon, where strong means a phenomenon is recognized, accepted by the field as having a particular nature, and weak, down at the bottom end, means a phenomenon may be ambiguous or contested or open. Now, the horizontal axis, the so-called discursive relations, represents fixed to multiple approaches to the phenomenon in question. So I translated this plane into the 5P model. Now, the top right, the purest quadrant, means there's a specific principle that everyone would recognize and associated procedures, such as voltage calculations in a system. Now, the bottom right quadrant, the doctrinal quadrant, is where it doesn't matter what the phenomenon in question is. What matters is the method, such as the scientific method or applying Six Sigma. Now, the top left quadrant, the situational quadrant, is the quadrant of possibilities, where there are a number of approaches to a particular phenomenon, like deciding on a control system, for example. Now, the fourth quadrant, the bottom left quadrant, is either because there's no clear phenomenon or approach, or the practice being observed is not about knowledge, rather it's about knowers, the people in the system. Now, each of these four quadrants represents a way of thinking, a code. And I believe you'll recognize the different disciplines tend to have dominant orientations, certainly in many of our curricula. Now, using this plane with 18 original problem-solving case studies, I looked at how a practitioner approached, analyzed, and solved a particular problem in a controlled electromechanical system in industry. So this gave me, as you can see from these, a whole range of problem-solving maps in different kinds of sectors, from contained systems environments, represented by these 4 case studies, to modular systems, meaning machine builders and systems integrators, to distributed systems environments, such as manufacturing, where you see many subsystems making up a whole, for example, production line process. Now, the key finding in the original research was that a successful practitioner is able to code shift. In other words, shift their way of thinking from fixed to multiple methods, from strong to weak phenomena across the problem-solving process. Now, the biggest problem that emerged across the case studies was this bottom left-hand quadrant, was dealing with people in a problem-solving system. And this problem was particularly acute in the manufacturing sector. You can see this no entry sign on each of these analyses over here. Now, I also observed that practitioners who have a different way of thinking, in other words, a different natural orientation, you can see from the top left here, the problem solver orientation was identified, that these practitioners in these environments experienced a code clash, a very different way of thinking to predominantly doctrinal environments. A number of them struggled so badly that they actually resigned from these environments. So let's just take a look at these environments. Let's take a look at manufacturing. Now, in South Africa, manufacturing is the 4th largest sector of employment. In other words, we need to be producing graduates that would actually like to go and work in these environments. It contributes 12% of our GDP, but it has had negligible employment growth in the past decade. And everywhere during my data gathering process in the manufacturing sector, I heard the same thing: skills shortage, skills deficit. Graduates lack the technical skills needed. So I thought, wait a moment, let me see if I can use the same analytical tool to look at how employers in manufacturing are dealing with this issue of lack of technical skills, or the whole question of technical expertise. The lack of technical skills is a problem, and this analytical tool was designed to look at problem solving. So very simply, using exactly the same principle, I created a coding system where companies either take a purist approach, in other words, they foreground discipline and practice-based knowledge expertise, and it exists, and actually it should be supplied by us, higher education. Or they take a doctrinal approach, standardized or generic training, or a case-by-case situational approach. In other words, they adopt a flexible approach to their needs. The fourth quadrant represented a people-orientated approach, where the company actually foregrounds the potential of existing human resources. So I'm currently analyzing 41 cases using this system, and slightly more refined. But for today, and with no claims to generalizability, I'm going to give you 3 examples. I have 3 manufacturing companies labeled A, B, and C, which range from large to medium. Now, Company A is a large automotive component manufacturing branch of an international company. They're under increasing pressure to remain productive and competitive. Now, there were 3 different case studies in this company, each with complex human factors. Now, to avoid local operator error, their solution is to integrate situation-specific automated systems which comply with the highly regulated doctrinal procedures at these particular companies. Now, this is the approach taken even when the most cost-effective solution is operator training. Now, I have reason to believe that their approach suggests a lack of faith in the ability of existing employees to adapt or acquire new skills. The second case is in the context of beverage processing and packaging industries. Now, here we have a medium-sized machine building company. They have a firm belief in expert knowledge, which requires standardized application in multiple contexts. In other words, a doctrinal approach. Now, this company is a South African company, and they value the small handful of expert technicians and technologists who travel extensively world over to install and maintain their machines. Now, these practitioners only pass on basic standardized protocols for the operators of their machines. And I quote from one particular participant, "The main thing is they have no skilled people. These people come straight out of school. Where do you draw the line about what I should tell them? The decision makers don't know anything about the machine, but I have to deal with operators who may miscommunicate what's happening." So this small handful of experts is aging. They jealously guard kind of the expertise they have, also not trusting the fact that they can hand this over to the very people who are going to be using the machines. And the company, because this problem is so dire, they've begun to move most of their manufacturing activities abroad, citing the lack of local expertise. Now, in contrast, a large locally owned beverage production company, which runs 24/7, has explicitly begun a training program that recognizes the dire need to upskill local capacity. In other words, they have a knower insight approach. And they recognize that they not only need to upskill or train their staff procedurally, they need to enable their staff to understand or develop conceptual understanding of the principles underlying the processes in this company. And I quote again here, "We believe that if they don't understand the machine, they can't even begin to fault find. And what we're doing currently to address developing understanding in the longer term is developing a number of courses for artisans." Now, these industry examples of how manufacturers approach the question of technical expertise present some useful insights for us as educators. Now, first of all, the epistemic plane, this tool as a whole, highlights the significance of different approaches to contextual problem solving, whether the problem is that of HR or technical. When applied to curriculum and pedagogy, as I have done in my research to date, this analytical tool really helps us to see the relationship between the what and the how of a problem. Now, for me, however, using this instrument to look at how different companies in the same sector approach the problem of expertise highlighted the kind of contextual complexity we seldom consider in education. Understanding a company's orientation to skills development alone may be important for graduates deciding on where to apply, Now, one striking feature with regard to context, which is currently emerging in my analysis, is who owns the company. And I'm going to tentatively say that in my current 41 case studies, the greater the percentage of local ownership, the greater the chance of legitimate investment in local skills development. Now, the second take-home message for this paper is the misrecognition of 21st century realities with respect to rapidly evolving technologies. Technological evolution outpaces the time required for learning. The statistics risk perpetuating notions that somehow the newer generations are not being educated properly. This is a global problem, and it suggests we have to see this in the context of a globally changing landscape. My third and final point is that in many of the companies I have visited, I see a lack of faith in what it is that we do. I mean, we have to applaud those companies who recognize their existing staff potential and who are designing and implementing training programs, but they're doing so in the dark, and many claim to be doing so out of frustration at what it is that we're doing. I believe we urgently need to regain industry's trust in our potential ability to equip graduates. This can only be accomplished through better education industry collaboration. And dare I say that I believe professional bodies need to join us in this, as well as a number of other key stakeholders. I'd like to suggest that if we do not regain the trust of our significant stakeholders, we stand to lose a great deal in South Africa. Thank you very much.